Hello everyone, welcome to my talk. I will be speaking about the Horo function compactification of the Muller metric. In this part in particular, I will be just introducing some concepts and some motivation to understand the second part. Mainly, I will be introducing some other compactifications and why I'm interested in the Horo function compactification in particular. Yeah, just as a warning, I will not be going over what Teichmuller spaces are, nor what the Teichmuller metric is in particular. But I should say this is not really necessary to understand the material, as I will be explaining everything from a metric point of view. That is, if you understand topics just geodesic, triangle inequality, and the exponential map, you should be fine. Still, it's good to know what the Teichmuller space is, of course, to get the motivation, but it's not strictly necessary. So with this, let's fix some notations. S will represent our surface, where I allow it to have some non-empty boundary and some finally marked points. Then Spirisoloi will denote T of S as the Teichmuller space associated to that surface. And MCG that will be the mapping class group. Just as a reminder, this acts on isometries on the Teichmuller metric. Just as a quick recap, the Teichmuller metric is one of the most interesting, most studied metrics that apply to the Teichmuller space. And one of the reasons is that going in a straight line is a rather natural action that you are interested more, probably if you look at Teichmuller spaces from a dynamic point of view, as going in a straight line is associated to doing the pseudo-Anosov map, so stretching in one direction and contracting in another, which is one of the reasons why Teichmuller spaces are interesting. So this metric is useful to study dynamics, of course, and essentially whenever you study dynamics, you're interested in the asymptotics. And so you want to study the asymptotics of these metrics. This is why compactifications come in handy, as they're a way of studying essentially the asymptotics. From a topological point of view, a compactification is just a way to add some points to a non-compact space to make it compact. However, from more geometrical and intuitive point of view, each of these points you're adding represents a way to diverge to infinity. And so this new boundary you're adding to your space serves as a classification of which ways the compactification allows you to converge to infinity and which ways it differentiates. So for example, the 1-point compactification, where you just add 1 point, this is one way of converging to infinity, and that's just getting away from a base point for any base point. And if that distance goes to infinity, then you're converging to what? To that 1 point. Another example is if you take the real line, one compactification you can do is by adding the 2 infinity points, and then you have 2 ways of converge to infinity. Either you go all the way to the left, or you go all the way to the right, and converge to the one infinity or to the other one. So let's actually see some compactifications for Teichmuller space. We begin with the most common one, and that's first-order compactification. And this is the idea behind this is to take the Teichmuller space and embed it inside the space of projection functions on the closed curves. And you do this by using the marking and given a hyperbolic function as a structure on your surface and a marking, you just send each curve to its hyperbolic length, the shortest of the isotropic class. Now, after doing some proofs, you can see that this is actually an embedding, and the space of projective functions is a compact thing. One defines the compactification as just the closure of the embedding. The action of the mapping class group can be extended to the space of functions on simple curves by just relabeling the curves. And this turns out to be an extension of the isometry, which is continuous. So you can say that the mapping class group extends continuously to the compactification. Now, this is actually a pretty good thing to have in a compactification, as the mapping class group is a rather interesting group. So you can either use the compactification to get information on the mapping class group, or use the mapping class group to get information on the compactification. Another interesting property about this compactification is that its shape is rather simple, and it just takes the form of a ball, where the boundary is just the projective measured foliations. Now, this rather simple shape makes it good for study, as you don't have to be worried about complicated topologies, just a simple ball. However, since the definition, if you go back, we haven't used at any point the geometry of Tegmore space. And as such, there are some quirks with the asymptotic metric. For example, if you go in a straight line that's in a geodesic, you may not actually converge to any. You may be converging to weird high dimensional sets as the complexity of the surface increases. You can find geodesics that converge to higher and higher dimensional sets. This makes it not ideal to study the asymptotic geometry of the compactification. So let's look at other compactifications that actually behave well with the asymptotic metrics. So the next compactification will be interesting is the visual compactification. Now, we're actually going to use this one, so we'll have to define it properly. But before defining it, let's explain a bit the idea behind it. And that's, so given a base point, you want to add all the geodesic rays exiting that base point in such a way that a sequence converges to a geodesic ray. If that sequence goes away from the base point, that's the distance between the base point and the sequence goes to infinity. And the direction you are looking at that point, at that sequence, stabilizes. What I mean by this, maybe it's more clearer once we do the definition. So let's do that. Beginning with the hypothesis. Now, of course, I need a metric space. Then I need the space to be proper. Then I need the space to be uniquely geodesic. This, as I said, I want to track a point going to infinity by the geodesics going from the base point to there. So I need that geodesic to be unique. Right? Then the next one, which is a bit of an unusual hypothesis, is that it has uniquely extendable geodesics. What I mean by this is that given any 2 points, there is a geodesic between them, a geodesic segment, and this segment can be extended in both directions uniquely. So there is just one by infinite geodesic that contains that segment. Now, these hypotheses are actually quite restrictive, so we cannot have any kind of graph except just one line. As soon as we have a point in here, then we will have this geodesic segment and this geodesic segment. So there is not a unique extension of this segment in here, for example. We can also not have any holes. As soon as we have a hole, then it will have 2 geodesics, either the one going above and going below. By the way, I should note, maybe I should have said before, by geodesic, I mean minimizing geodesic, not locally minimizing, so the metric global sense of a geodesic. So once we have the hypothesis, we can go to the actual definition. So the idea is to paste the geodesics exiting the base points to our space. So the first thing we have to do is choose a base point, and we just do it at the beginning. And once we have chosen a base point, we take the set of directions exiting B. This will be labeled D sub B. This geodesics geodesic rays, so from 0 to infinity, going to X, such that gamma of 0 is equal to B. So now we want to paste this set of directions to our space, and we will be doing this by using the exponential map. Now, if you remember anything from your Riemannian geometry courses, this is the same construction. So you take the set of geodesics, and then sometimes you quotient it by the origin, and you send gamma t to just gamma of t. Now, by the hypothesis we have required, this is actually an homeomorphism. So we can compactify X by just compactifying our space in here. And we will do this by just adding the point at infinity. So we will have that the visual compactification based at B will be defined as this space in here with the usual topology. This could also be written by using this homeomorphism here as X union dB, where this dB will actually be the dB times infinity. So this somewhat technical condition actually reveals a rather simple shape, right? As we are taking the sets of directions, which actually is homeomorphic to the sphere at distance ones, and just expanding it towards infinity and towards zero. So we will always have a ball as a shape. Also, it's a bit harder to see, but not that hard, that the geodesic rays actually do converge to points. And so you have that these two properties in here are satisfied for these compactifications. However, in the definition here, we did require a base point to define the compactification. And the final result, the final topology you get on your space does depend on the base point you choose. As such, if you have any action that moves this base point, you might not be able to extend it to the boundary. As you move it, you change the topology, and it's difficult to extend the action. This happens to be the case for text-model space, and this was put in by Kerckhoff a long time ago, and it makes it so it's not that good of a tool to use to prove results, as you don't have the action of the mapping class group, so you're somewhat limited in what you can actually do in it. However, it's still a great thing for visualizing things from an intuitive point of view. And while it's not used for proving stuff, many results are stated in terms of the visual compactification, as it helps understanding more or less what is happening. Finally, the last compactification we'll be talking about is obviously the Horo function compactification. Now, we're also going to be using this one, so let's define it properly. The first things you will note are that the hypotheses are much smaller than before. You just need a proper metric space. And so the idea behind this compactification is to take the space and put it inside the space of listed functions in it by taking a point and sending it to the function, the distance to the point minus the distance to a base point. Now I'm choosing here a base point, but the result will not depend on the base point. The topology will be the same, whichever base point we have chosen at the beginning. Since X is proper, one can prove that the space of listed functions is actually compact. And furthermore, that this inclusion here is actually an embedding. And so we can define the Horo function compactification as just the closure of this inclusion in here. And that's essentially the Horo function compactification. Now, this rather simple construction results in a rather powerful compactification. And one of the reasons is, as I said, the hypotheses are really minimal. Another one is that after proving it a bit, you can see that isometries do act by homeomorphism, this compactification. So you can extend isometries to the compactifications in a good way. So in the case of text-model spaces, you will have that the mapping class group does act in these compactifications. And then the other one is that it's well suited to study the metric. In fact, it is sometimes called the metric compactification. And in particular, you do have the geodesics to converge to points. So the first two properties will be satisfied for this compactification. The main drawback, however, is that the construction is a bit abstract. And you can see it just from here. It doesn't really tell you what it means to converge to the boundary. You don't have a shape directly from this construction. And it's kind of not really known what shapes it takes for text-model space. And this is what I will be talking during the second part of this talk. Now, the thing I will say now is that it's not a sphere. This was already known. However, it will contain a sphere. So which shape more precisely will be, I will discuss this in the second part. So see you there.